Okay, so this is to finish the last part of the notes packet on polynomials. All right, and we're going to talk about maxima and minima. Okay, so maxima is plural for maximum, and minima is plural for minimum. And sometimes these values are referred to as extreme values or extrema. And we have two definitions here. So we have this curve here, and it says that for any function f, if there exists an interval x1 to x2 that contains c, so that for all x values that are not c in the interval, f of c is greater than f of x. So it's greater than all the y values in an interval around it. Then we would call c a relative maximum or local maximum. And we have two spots on this graph where we have local or relative maximum points. Okay, so if you can draw a circle around it and there's a highest point in that interval, okay, so that it's higher on points on both sides of it, then that is going to be a relative maximum. A relative minimum, same thing but reversed. You want all the y value to be less than all other y values around it. So we have a local minimum here. Okay, so this would be a local or relative minimum value because it is the lowest y value on both sides of it. Okay, so let's look at the example. It says at a local max, the graph changes from increasing to decreasing. On the graph at the right, shade the intervals of increase in green. All right, so let's get a little highlight going on here. So we are increasing along here. Okay, we are also increasing along here. Okay, and then it says at a local minimum, the graph changes from decreasing to increasing. So on the graph at the right, shade the decreasing intervals in yellow. Okay, and then we can see this is where we change from increasing to decreasing. So this is a local max. And then from decreasing to increasing, we have our local min. Okay, so let's take a look at the intermediate value theorem. All right, so this theorem states that if you can find two y values where the sign changes, so if you look at this blue curve here, okay, if we look at the y value at this point right here, you can see you're below the axis, you have a negative y value. And then if we look at the y value when x equals b, you see you have a positive y value. Okay, we know a 0 must exist somewhere along here as long as the curve is continuous due to the change in sign. Okay, because we're going from negative to positive, we know at some point in here the function must equal 0. And this is a theorem you will use next year quite a bit in calculus. So example 4 says, use the intermediate value theorem to explain why this function, g of x equals x squared plus 3x minus 6, must have a root x-intercept on the closed interval 1, 2. So in order to use the intermediate value theorem, we would want to evaluate this function at 1, and we're going to evaluate this function at 2. So at 1 squared plus 3 times 1 minus 6, we get negative 2. If we evaluate it at 2, we get 4. So because the y value is negative at x equals 1 and positive at x equals 2, there must be a 0 in the interval 1, 2. What is going on here? up. Okay, concavity and points of inflection. So looking ahead to calculus, we need to talk about concavity. Our goal today is understand the terminology for now, and then later we will have calculus rules for finding these intervals algebraically. Okay, so it says a function f is concave up on an open interval I if for any choice of x1 and x2, with x1 being to the left of x2, the graph looks like a U, okay? So U-shaped concave up, so on this interval, all the way over here until about here somewhere, it looks like we're concave up, we're U-shaped, or we look like a smile. Okay, it also says a tangent line will be below the curve if the function is concave up. A tangent line is just a line that would touch the graph at one point. So if I draw a tangent line so that it touches at one point here, you can see that the tangent line is below the curve. Okay, a function is concave down on the other hand. On an open interval I, if for any choice of x1 and x2, with x1 being left of x2, the graph looks like an upside down U, or a part of a frown. Okay, and it says a tangent line would be above the curve in this case. So if I drew a tangent line on this side where it touches just once, or almost touches, you can see it's above the curve. So that would be concave down. And the function f has an inflection point. Okay, that's where it changes concavity. It has an inflection point at C on an open interval if the graph changes concavity. So for now, we just need to know these terms. Okay, and then we have one more example to look at, example 5. Okay, so we have this graph here, and we want to find the intervals of increase. Okay, so intervals of increase, let's start with yellow. So increasing, it looks like here and here. So we could say those values of increasing are from D to E and from F to G. Okay, decreasing on the other hand, looks like here, here, here. So we could say 8B, E to F, and G to H. Okay, and it looks constant along here. Okay, so we could say it's constant from B to D. Okay, it says mark and estimate 2 points of inflection. So we want to estimate where it changes concavity. Okay, so we've got a concave up here, a concave down here. I would estimate right around here. Okay, and then it goes concave down again, so maybe around here. All right, it says the graph is concave down. Okay, so we'll name this one K and this one M. All right, so we're concave down from K to M, right? And we're concave up. Well, we don't quite have enough points. Let's name this N. So N to K, we're concave up. Okay. It looks like we have a relative max at E and at G. And we have a relative minimum at F. And that's the only relative minimum I see. Okay.